Okay, well, welcome everybody. Welcome back. We now have part two of our topic three, illumination of the workplace. And this one is on a particular equation we call Lambert's law, written by Lambert the Lamb. Okay, so we're going to get to Lambert's law, but first we talk about the relationship between E, illuminance, right? If you don't know what I'm talking about, go back and watch 3.1 again. E stands for illuminance. That's the amount of light energy that strikes a surface. That is related to the luminous intensity of the light source, abbreviated with an I, and that is the amount of energy that is emitted in a particular direction, like lumen per steradian candela. All right. If you need a minute, you can go back to 3.1 and watch it all over again. I know it's confusing, all these terms, but I'll go slowly with that. Okay, so there is a relationship here. It is an interesting relationship that for a given intensity, luminous intensity I, the illuminance is related to the inverse square of, it's inversely related to the square of the distance between the light source and the surface. Okay, so this light bulb casting light, off into infinity until it strikes a surface, over half a meter. This same luminous intensity, the luminous intensity never changes. It is basically, it is directly related to the luminous flux, which is a property of the light source. So the luminous intensity is a constant factor no matter where it is, but the amount of that light energy that strikes a surface is usually what we're interested in, the illuminance. So what we are seeing here is over a shorter distance, we have a higher level of illuminance, 40 lumens per meter squared, or 40 lux. Lux is lumens per meter squared. And then if I double that distance, the illumination actually becomes a quarter of that same value. So again, it's related to the square of the distance. So you double the distance, 1/2 squared is 1/4. That ultimately is why, this works out mathematically here. Okay. All right. So again, as I mentioned, the intensity of a source is assumed to be constant. And if you are then able to measure the illuminance at a certain location, by the way, I do have my photometer that I promised that I hope to bring. So, all right, here's what we got in my office currently. Looks like, if I hold it up to the light at least, looks like I'm at about, I have to read the manual, but what I will show you is that it's at about 20% of the way. And now I'm going to go and point it out my window out here. It goes off the chart immediately, goes way off the chart. So much brighter outside. Again, this is a photometer. This is a fairly old photometer. I would guess it's from it's at least 3 or 4 decades old, I would guess. But it still works just great. And yeah, light meter, so we can determine the foot candles in this. That's illuminance, right? So illuminance, E, is what we're talking about. And if we are measuring that right here, if I'm interested in just this light source, so if I had a way to block out all the other light sources except for one in a space, and I got out my photometer here, and I said, okay, well, under here, I get 35.6 foot candles. Now, with that knowledge and knowing the distance that I am from that light source, I should be able to know what I need for how much luminous intensity is at that light source. And then if I know any other distance from that same source, I can then calculate what the expected illuminance would be. So if I've got E at one spot and I've got D1 and D2, I can solve for E2 like this. Okay. So there you go. So again, and then this is just, again, because the property, if you go back to this, the property luminous intensity, I, is going to be constant. Okay, so then if I've got E of a certain, I'm measuring E at a certain location, that's with my photometer, and it's at a certain distance, and I square that distance, that's my, that's my common factor here. And so then now I know, as long as I stays constant, which it will if it's the same light, this will hold true, this relationship. There we go. So yep, I move it up there, G2, there we go. So then I should be able to calculate that, and that's the kind of thing I'll ask you to do on your homework. So what would the illuminance be on a different location in this room? If you were to, I think the example I usually use is the light on a desk, and well, what if you have an assistant's desk that is 4 feet away? How much light is going to be on that surface? All right. Because it matters. Sometimes we need to calculate how much illuminance do we need to do certain types of work. And this is something that we can find actually in our military standard. We'll be using that later in this topic. All right, so just quick we'll work out the math here just as an example. Let's say 10.0 lux. Remember, lux, lumens per meter squared, lumens per foot squared, are typically what we refer to as foot candles. Foot candles and lux don't sound very similar, but they are basically SI and British units. So lux, we're talking illuminance. And if I've got 10 lux, what would it be at 1 meter away? So if I go, at half the distance, and so I can use this equation, I can rearrange it. I can then find out, 40 lux. And guess what? That's what we just saw here, right? So, if I go half the distance or twice the distance, and it's I'm sorry, if I start here and it's half the distance, it should be 4 times stronger, 4 times more illuminance. There we go, 40 lux. Okay. All right, good. So now we're going to break down the units here, make sure that makes sense for us. So total luminous flux, remember this is my putting your hands around the entire star example. If you had giant hands and that thing hovering in the middle is the sun or it's a star, and you're absorbing all of the energy emitted from it, that is the total luminous flux. You would say, I'm getting sunburned on the palms of my hands with this much energy, all of the energy emitted from the sun, total luminous flux. Again, not all of that goes in the direction we're interested in. That's why we have luminous intensity, I, and illuminance, E, which is how much of that light is on something I'm interested in. So if we then go back to our units, and again, if you want to pause this and go back and watch 3.1 again, check the units with all of these measures so you can get them straight. I know it takes iterations of this. But if we talk about illuminance in lumens per meter squared, again, we could have lumens per foot squared. And again, that's foot candles. Lumens per meter squared right here, also known as lux, L-U-X, right? So maybe the more I say that, the more confusing it gets, but I'm hoping it's iterations and you can see the relationship. So yes, I've got lumens per meter squared. Now I am multiplying by a surface area. And if I can define that surface area as, the inside, the palms of my hand, right? As I cover this thing, I say, okay, that's in meters. That's in square meters because it's a surface area. It's not a volume. And so then I can say, well, how much energy am I absorbing now from this star source if I am 0.5 meters away from it? And so let's say that's, I determined that's 40 lumens per meter, that's 40 lux, like we were using in the previous example. So now we'd say, well, what's the surface area at 0.5 meters? And we can actually do the geometry, 3D geometry equation. This is the surface area of a sphere is 4 pi r squared. And so that, turns out if you use 0.5, square it, it is 1/4. So these cancel out. So, you get essentially pi meters squared. Okay, so that's our answer. so far, that's the surface area. So now how much of this energy over that surface area, now if we divide by the surface area that is striking, this is everything that that energy is striking. And so if we want to know what is the total source energy, the total luminous flux, and we can measure, oh, well, I know with my photometer, I can measure illuminance. I can't really directly measure total luminous flux. I can only measure how much energy is striking this thing right here. And then I got to work backwards through my equations here to determine, okay, well, here is the total luminous flux of this light source. So that would be 125.7 lumens. And again, this is all the energy, okay? So if I was talking about luminous intensity in one direction, it's a fraction, it is a steradian of this energy, right? It is not all the energy, because here's the source of light. I'm only interested in the light going this way, not all the light going in all the other directions, okay? So there's a different, I know I'm iterating on that several times, but I do want to make sure we get that straight, okay? Now here's the interesting other point. So if I wanted to check, you know, the total luminous flux doesn't change. It is a property of the source. And so if I measure at different distances and I do this reverse sort of equations, I should get the same answer. And indeed I do here, right? So at 1 meter away, you know, from what we were, I guess this is based on the same values we were using in our previous example. You know, if I go from 0.5 meters away to 1 meter away and I have larger hands that can still get around it, and then I see, okay, well, this is 10 lumens per meter squared. Now I have a larger surface area in terms of meters squared of my larger, you know, sphere surface area. And so I use the same equation, 4 times pi times 1 meter squared times 10, and I get, yes, I get the same value. That makes sense because, again, it is a constant property of the light source, is this total luminous flux, how much light can it put out. Yep, so there you go. The total luminous flux is a constant, it's a property of the source. Don't forget that, so it won't change. Okay, so another factor that we have to think about with, you know, how much illumination are we getting on a surface is what we call the angle of incidence. So this, I think I'm illustrating it fairly well here. If I shine a light directly at something, all of that light energy is striking that object. It will have a greater illuminance than if I take that same light source and I come at it from an angle. So the more I go to the angle, the less illuminance I get on the surface I'm interested in. If it's completely orthogonal, completely you know, perpendicular to the surface, that's going to be the maximum illumination. If it is parallel to the surface, and imagine this, if I have a laser beam of light, you know, flashlight, and I shine it and it is parallel with the surface, the light beams will never strike the surface. So you have effectively an illuminance of 0. All right, so again, this is the angle we're talking about. By the way, do I have it in here? I hope so. This angle is our angle of incidence. Now note, not this angle, okay? This is really important. Very commonly, I see errors in homework, in whatever, where the wrong angle is used, the complement, essentially, the 90-degree complement of it. So you need to know the angle that is the difference from the normal line. Okay, so this is here's the surface we're talking about. Here is the normal line. It's perpendicular. It's orthogonal to the table. From that line to a radial line from the source to the location you're interested in. Okay, that's the angle that you need to have, not that angle. Very good. All right. So with that, yep. So I think I've already kind of explained this. If I am totally perpendicular, if my angle of incidence is 0, that would be this, because it's here. Let me draw it. The angle of incidence here. Well, there is the line from the light to the source, and here is of course, the perpendicular line. The angle between those two is 0. 0 degrees is our angle of incidence. The angle here might be 90 degrees in this case, right? So if it's, if that's 90 degrees. So we get to then use, turn this off. Sorry. Clear all drawings. Okay. All right, so this matters because, yeah, here we go. All right, so 70 degrees. So when we know this angle, we get to, put it back into our inverse square law equation, and we get the full version of Lambert's cosine law. So it's taken a while for us to get to what is Lambert's law. Remember the Lamb at the beginning. So this obviously the scientist. Cosine is going to be part of our equation, and again that factors into the angle of incidence. So cosine of 0 is 1, and so then the multiplier is 1. If a cosine is 90 degrees, that value would be 0, and you effectively have 0 illuminance. Okay, so full illuminance, 0 illuminance here, and everything in between. So here's the equation, and you'll note we have luminous intensity and distance squared. We already had that. And so we're basically just adding to this, or not adding, we're multiplying by this cosine of theta factor in order to account for that angle of incidence, okay? So this is the most basic form of this equation of Lambert's law, Lambert's cosine law, that relates illuminance and luminous intensity from a light source if you know the angle and the distance between the light source and the surface that you're testing the illuminance on. So there it is, full illuminance, full illumination when it's the surface is normal, 0 degrees, cosine is 1, 90 degrees, cosine is 0. All right. Okay, so taking this law to the next step. Now, I already said the most basic form, the most fundamental is what we just showed. This one here, the I times cosine of theta divided by d squared is equal to E, illuminance. Now, all of these equations make an assumption that the light source has no dimension and is a pinpoint of light that emits in a spherical direction. That's sort of the assumption here, or it's at least that it's a point relative to the field of the line of sight from the light to the surface you're interested in. However, very commonly this is an inappropriate approximation. So you can imagine, this light in my office right now is an elongated source. It does not act as a single point of light, which would be real easy for my equations. This is an extended source. It's like there are, infinite points of light along it, and each of them acts independently on illuminating this space. So that's obviously, like impractical to say I'm going to approximate infinite points of light. So we have some corrective, empirical based corrections. And so I'm going to teach you how to correct for these elongated, extended sources. Okay, so very commonly these days, light is not provided by a single point of light. In this office right now, it is, right? Even if I was to talk about what's the light coming from this window behind me, I need to consider the entire dimensions of the window, because this is different than a point of light that is emitting that much light into my room. So we have correction factors. Okay, so the first one, we need to know, hey, do we apply a factor or not? And so the first thing we ask is, this is the rule we apply, the 5 times rule. It is a rule of thumb. This is not based on anything deeply scientific other than empirical. We need to have a rule, and we can kind of see that, okay, well, there's infinitesimal, there's very small precision difference, so we can approximate this way. All right, so if the largest dimension of the source is at least, if you're at least 5 times the distance away from a light source as the longest dimension on that source. So let me break this down. If this is the light source, this one right here, actually, let me use this one. I would say the longest dimension. So, this dimension, the width is not the longest dimension. the length is the longest dimension. Technically, and I won't mark this wrong if you do it, if I were to ask you about something this large, technically the longest dimension is actually the diagonal here. You could do that. I think it's okay to just say the longest dimension is the length here, and to be, that's a good approximation. So anyway, that's the dimension we're interested in. If I'm not at least 5 times further away, so this light here in my office right now is probably about 8 feet long. That means in order for me to treat this light with the same equations we were just using that assume a point source of light, I need to be at least 5 times 8 feet equals 40 feet away from it. I'm not 40 feet away, so I cannot treat this as a point source. However, if I had this little tiny light bulb, and let me tell you, the largest dimension in this light bulb is the width, or the length, I should say, of this filament. So what's emitting light? It's not a single point. It's actually this filament right here. And that has a dimension to it. It has a length. So that is the dimension. It's maybe 1 inch, okay? So what that says is if I am at least 5 inches away from that light, I can treat it as a point source. I can use Lambert's cosine law. If I'm not at least 5 times the distance of the longest dimension away, that's when I apply a correction. And we've got the correction coming up next. All right, so clear light bulb, the largest dimension might be the filament itself. If you can see, if it's unimpeded light coming from the filament itself, then that's the longest dimension. If we have a frosted bulb or, a globe like this, this is an example of something we call diffusion of light. And so what this does is it takes, the total luminous flux from, this element, and it essentially spreads it more evenly. There's some loss of light energy, but it makes a much more uniform and pleasant illumination experience. Now, if I look at this bulb, though I don't see the filament inside, to my eyes, the longest dimension is probably the diameter of the bulb. Okay, so that's what I'm thinking of. The diameter of this frosted bulb, or if you can see it, the smallest. If you can see the element itself, it's the longest dimension of that element. Okay, there it is. Yeah, thank you. Yeah, and this can be, of course, it's not. I hope you remember this then also from the topic 2 homework. It's not only in one dimension. It's any dimension that is, within my line of sight, a measurable, projection. Okay, there we go. So here's our correction factor, K. If we fail the 5 times rule, so if you pass the 5 times rule, meaning I'm at least 5 times away from the longest dimension, then you can say, great, I don't need any correction. If you fail that rule, meaning I'm closer than 5 times that longest dimension, got to have a K factor. And this is an empirical factor. Okay, so this has been, basically documented by people collecting thousands of data points and seeing what it says and then saying, okay, well, here, this must be that relationship. So this is the graph that I will ask you to use. And by the way, if I had my soundboard, bookmark this. You're going to want to use this for your homework, for your quizzes, for your exams involving this topic. You want this graph. And basically, you find the ratio between these 2 distance measures. So, this little d being the longest dimension of the light source, and big D being the distance between the light source and the surface that you're interested in, or what's the illumination on this surface. Okay, so if you know those 2, then you come up with the ratio between those 2. So you literally little d divided by big D, and find where that is, on this scale. You'll notice, like, hey, 5 times rule, right? So that the 5 times rule says I am at least, if D is at least 5 times, if big D is at least 5 times what little d is, then this is going to be something in the, like less than 0.2. And it's effectively, that's where we approximate and say that's pretty much a 1. That's pretty much like no correction needed. But what you'll find is a lot of these ratios end up in this kind of between 0.5 and 2 range. And that has a pretty dramatic effect on how much this multiplier changes. So you literally, you find on the d-axis, on the d over d axis, you line up with this this curve, and you see what the y value is, and that's your k factor. All right, so here's a practice approximation here. There's our luminaire. Let's say it is only 2 feet long and it's 8 feet above the work table. So far, just with those first 2 lines, I should be able to apply the 5 times rule. Go ahead and think for yourself. Do we pass the 5 times rule? Do we fail it? Okay. The answer is we're failing the 5 times rule because we take the longest dimension here, 2 feet long, and we multiply that by 5, that'd be 10 feet. We are not at least 10 feet away between the surface and the light source. So it needs to be at least 10 feet if we can treat it like a point source. We're not that, so we need a correction factor. We're gonna have to go to that K chart. Okay, so imagine this. I take my luminaire, I put it right under, like directly under the light. It says I've got 35 foot candles. Okay, that's illumination, the illuminance on that surface. What is the equivalent point source luminous intensity? So I now need to say, well, what, I know what my photometer says right here, but we know we need to approximate this for what's the illumination of this whole space. 5 times rule, we fail, right? So we fail it. So our K factor then becomes, we need to know those 2 distance values of the little d and the big D. And so 2 over 8, and we get 0.25 there. So I then go to my graph here. I find 0.25. I find where it crosses on, where it meets the curve, and what's the K value there, and it's about 0.9. You're going to basically eye this on the chart. There isn't a direct way to plug in a number and get a function output. So there's going to be some room for fudging here, but do the best you can with this approximation. Also, this is an important thing. Note that these are in units of 0.5. So it'd be very easy to get, not paying close attention and miss that, that's a 0.5, that's 1.5. This isn't, okay, you get it. You can just look closely. All right, there we go. So if I got 0.9 as my correction factor, now I plug it into our Lambert's law, and I've got a value for K. I am going to now, what is the equivalent point source luminous intensity? I'm solving for I. I'm asking about I. That's what luminous intensity stands for. So I rearrange this equation. I should know all these things. I do. I know what my photometer tells me. I know that it is 8 feet. So big D is 8 feet. Don't forget to square it. Commonly people forget, but remember, this is the inverse square law. You have to square that distance to be, to work with this equation. And then I've got the K factor of 0.9. I also know, because I'm going straight down at the table, I put the photometer immediately directly underneath this elongated light. That's how I know the theta, the angle of incidence, is 0, and cosine of 0 is 1. So that's where that came from. What's my answer here? 2489 candela, mathematically equivalent to 2489 lumens per steradian. Okay. So that's a typical value. If you can think of, this is a property of that elongated light if it were approximated as a point source. All right, let's take the same numbers, 35 foot candles where it is right there. And what if we move this 4 feet to the edge of that table? So the light doesn't move, but there's a couple things that change here if we do that. Okay, so first of all, you'll probably note, actually, let me do it this way. Pause, review the equations, see if you can solve this problem. What would you expect? And then I'm going to go through it here on the next slide. So pause and do that. Welcome back. Okay, so I'll give you a few hints. You can pause, and then if you get just a hint, and then you can finish it. Pause it real quick. All right. Don't forget, I is luminous intensity is a property of the source. It remains constant. So if I measure here and I measure here, I should come up with values that ultimately, if I were to, reverse engineer, I should get the same value of I, just like when we got it right with this example, right? Same value of total luminous flux, also the same value of luminous intensity when you have the same light source. Okay. All right, hints. Okay, oops, sorry, I have to move it back. There we go. All right, I is a property of the source. There's a new distance value, and it's not 8 feet, and it's not 8 feet plus 4 feet, but it's something else that an engineer can probably figure out. Do we still fail the 5 times rule with our new distance? If we do we need a new value for K? Okay. The photometer is no longer normal to the source. It's not directly under it. It is now at a slight angle from that source, and that angle has to be factored in, right? All right, so here we go. This is our equation. That's my calculation. That's my answer, 25.6 foot candles. Makes sense because I would expect to go from 35 foot candles, and now I'm moving it away from directly under the light. I would expect the illuminance to decrease by a certain amount. So mental check, that seems good. Now, I'm not showing you all the details here. Oh, I guess I do. Sorry. So with 25.6, I actually worked out the details in an Excel file that I posted on campus under, I think it's under like supporting materials in this module, in the topic 3 module. So if you want to check out that Excel sheet, you can see the equations that I'm using in there too, and that might, that might be useful for your assignments or whatever. But this is how I got to those 25.6 foot candles, so you can work through it yourself, see if you get a similar answer. If you get something different, let's talk in office hours. All right, thanks. That's topic 3.2.